Alright, so today we're going to talk about motivating the Schrodinger equation. Now, the Schrodinger equation can't be derived in the normal sense, just like you can't derive Newton's laws. But as we're going to see, we're going to be able to find a very good motivation to see why it's a reasonable thing. So, to motivate the Schrodinger equation, I realize there's an extra O in there. I don't know how that got there. But, just like in classical mechanics, we want to be able to evolve the state of a system. So, in classical mechanics, if I tell you the position and momenta of all the different particles in your system, you can evolve the state using Newton's laws. So just like in classical mechanics, we'll also be able to do that in quantum mechanics. So the Schrodinger equation is going to, if you have a state, you can evolve it forward in time with absolute certainty. So although you can move it forward in time, it's still a probabilistic description, because the wave function squared itself is the probability distribution of your particle smeared out in space. So, although the equation is going to be deterministic, we're still using a probabilistic description of the system. It just happens that we can evolve it forward in time in the usual fashion. So, to motivate the Schrodinger equation, because whenever you first see it, it looks like just a bunch of letters thrown out on the page. We're going to consider a wave packet that looks like this. So, some exponential e to the I, and then kx minus omega t. This is going to be a plane wave that's moving right in one dimension. Now, we need to take this with a grain of salt because this wave function is not normalizable. If you take the norm squared of this thing, then you have a probability distribution that looks like this. And as you can see, you're not going to be able to normalize this. So to do this a little bit more formally, you would have to construct a wave packet, which would be a superposition of plane waves, which is going to be related to the Fourier transform. But we won't get into that, because we just want a simple motivation of the Schrodinger equation, and this is going to do. But keep in mind, because this will come into play whenever we talk about the free particle, but you can't normalize a plane wave. But it'll serve as good motivation to find what form the Schrodinger equation should take. So if we act on psi with h, our energy operator, like we said in the last video, well, we said the energy operator is going to be the momentum operator squared, so acting with the momentum operator twice, over 2m plus v, where v is just our potential. Acting on psi, well, that's going to be negative h bar squared over 2m, second derivative with respect to x, plus v, acting on psi, because the momentum operators we discussed in the last video is equal to h bar over I, partial derivative with respect to x. So if we act with that operator twice in a row, well, we have an h bar squared, and then over an I squared, well, that's just negative 1. And then if I take the derivative twice, that's just going to be the second derivative. So what do I get whenever I take the second derivative with respect to x of this wave packet? Well, if we look at the form of the exponential, we're only looking at the spatial part. So if I take the derivative with respect to x, then I'm going to get an ik out front from the first time I take the derivative. But then, if I'm taking the second derivative, then I'm going to get another ik. And then just expanding this out, then if I have I squared, well, that's going to be -1. And then I'll have a k squared as well. So when I put this back in, well, I'm going to have h bar squared times k squared. And then I have a -1 out here from acting with the momentum operator. But then I also get a -1 from squaring this. So it'll be positive h bar squared k squared over 2m plus v acting on psi. We can do this algebraic manipulation because the energy operator is a linear operator. So I can act on psi with the first part of it and then factor it out because I end up getting psi back. So if I look at this top part, well, if we remember the de Broglie relationship for waves, that P is equal to h bar k, then I've got P squared on top because I've got h bar squared k squared. So I've actually got P squared over 2m plus v. Well, what's that equal to? Well, if we remember from classical mechanics, that's just the energy of the system. So whenever we act with the energy operator on psi, we just get the energy of the system times psi. So if we want to see how psi changes with time, because I said we want to evolve our state forward in time, well, hopefully we'll be able to find a way to relate the two. Well, if we take the partial derivative with respect to t of our wave packet, now we're looking at the time part of this wave. Well, then I'm going to get psi, because it's an exponential, times the negative I omega. Well, this isn't quite the energy of the system out here, because first I've got an imaginary number, and then the de Broglie relationship says P is also equal to h bar omega. So I need an h bar out front, and I also need this I to go away. Well, if I multiplied that operation we just did by I h bar, then what would happen? Well, I would have a negative I squared, but I squared is -1, so I end up getting a positive 1 times h bar omega. H bar omega psi. And then that would give me the energy of the system times psi. So I would be able to set I times h bar partial psi over partial t equal to the energy operator acting on psi. And so this is the time-dependent Schrodinger equation. And like I said before, this isn't a proof, so to say, in the normal sense of the word, but it's very good motivation to think why it must be true. Just like we can't derive Newton's laws or derive the principle of least action we can't derive the Schrodinger equation. It's a postulate. But if we look at it this way, in a conservation of energy sense, because we had to equate the two energies, then the Schrodinger equation seems like a reasonable model. And it turns out that it is. It fits the data pretty well. So, the next few videos will be playing around a little bit more with the algebra of operators, and then also using the Schrodinger equation and the harmonic oscillator. So, I hope you liked this video. Let me know in the description if you did. See you in the next video.